Hello, and thank you for taking your time to view our video presentation on our Mechatronics project, which is the PLC controlled fertigation system for crop management. This presentation is brought to you by the members of Group 1, which include myself, Lim J, Muhammad Aiman Haikal, Zakwan Akmal, Faiz Hakimi, and Wan Hafizuddin. So to start off, I would like to give a bit of a background on our project. The global food system faces a critical challenge driven by a growing population an increasing scale of farmlands, demanding optimal resource utilization while maximizing crop yield and equality. With the current traditional agricultural practices, this relies heavily on manual inspection and inefficient blanket application of fertilizers, which are fundamentally inefficient. This outdated method is labor intensive, leads to significant resource waste through over application, causes substantial environmental runoffs, and ultimately results in inconsistent crop yields. This method is fiscally and environmentally unsustainable. So the core issue lies in the reliance on predefined schedule based nutrient supply. Even with advanced methods like conventional fertigation, optimal crop health requires a definitive shift from these time based deliveries to a precision nutrient supply driven by real time data. The plant's demand for essential elements like nitrogen, phosphorus, potassium, or just water changes dynamically based on soil moisture, temperature, and specific growth stages of the plant. The current schedule based model fails to provide the precise control needed for optimal nutrient uptake, often resulting in either nutrient deficiencies that impact the yield or environmentally damaging excesses. To ensure resource efficiency and maximize potential crop output, we must implement a system capable of making rapid, data driven decisions based on current field conditions. So, as a solution, our project achieves this by implementing an automated, intelligent precision fertigation system, which is controlled by a PLC or programmable logic controller. This system is designed to entirely replace scheduled delivery with dynamic real time control. The PLC acts as the central brain, processing live data from field sensors to help calculate and deliver the exact nutrient concentration required at any given moment. This closed-loop control system guarantees that the crop receives the optimal level of fertilizer, maximizing yield potential while eliminating waste through over-application. This implementation of precision agriculture directly supports the United Nations Sustainable Development Goals or SDGs, specifically SDG 2, Zero Hunger, through increased food production, and SDG 12, Responsible Consumption and Production, through optimized resource use and minimized environmental impact. Moving on to our problem statement. In crop farming, there is a constant requirement to monitor crop growth. Given the ever increasing size of modern farms, the conventional method of manually inspecting each crop lot becomes impractical. An automated system should be developed to ensure proper distribution of fertilizer, mineral, or nutrient solution to each crop by utilizing sensors to monitor soil composition and plant conditions in real time. So moving on, here are our project objectives and deliverables. So first off, we have the literature review, which is to conduct a review on the demands of the agricultural industry, existing fertigation systems, and industry standards to establish the functional and performance requirements for the proposed system. Next, we have the identification of major components. So this is to identify major hardware components required for the system and define the sequence of events, the input and output mapping that is required for our PLC control system. Lastly, we have to develop a PLC ladder diagram. So we have to design and develop a complete ladder diagram that defines the control logic and outputs for implementation into a PLC further down the line. Thank you, and I will pass this to the next person.
The first part of the literature review that I'll be covering is about the impact of moisture, pH, and the NPK levels on plant physiology. First of all, controlled irrigation, which is 70% level, for example, maximizes water use efficiency and optimizes nitrogen uptake, resulting in superior growth traits like plant height and crop weight, according to Abaza et al. The second part is Maintaining optimal pH is crucial for unlocking nutrient availability and balancing the rhizosphere microbiome, which supports healthy antioxidant enzyme activity and reduces plant stress, according to Zia et al. And finally, optimal NPK ratios enhance nutrient use efficiency and soil health by regulating physiochemical properties like electrical conductivity and available nutrient reserves by Vina et al. The next literature review is about sensor-based automation in fertigation, the limitations of conventional and time-based systems by Atian et al. Traditional agriculture relies heavily on manual or time-based open-loop irrigation. These methods fail to account for dynamic environmental changes, resulting in significant water and nutrient waste due to over or under application of water. Field trials confirm that sensor-based automation outperform manual methods, achieving 43.74% to 45.25% increase in crop yield while simultaneously reducing water usage by 7 to 12% and fertilizer consumption by 15 to 25%. The evidence supports shifting from timer-based to sensor-based control to enhance agronomic efficiency. This directly justifies the project's objective to utilize a PLC for real-time control to maximize yield and minimize environmental impact.
So for this project, we have four major components, which is control units, sensors, actuator, and hydraulic system. So for control units, this is where the PLC or programmable logic controller is located. It acts as the system's digital core for automation and management. So it continuously program with logic base such as time, volume, and sensor readings. So the function for this control unit is to receive the sensor data, process it, and then give outputs commands to the actuator in real life. So for sensor is the input device for this project. So it transforms environmental or psychological conditions into electrical signal for the PLC. So uh, in this project, we have four sensors, which is soil moisture sensor, which determine exact irrigation needs to prevent over or underwatering, flow meters, which provide feedback on actual volume of water and fertilizer delivered, electrical conductivity sensor or EC sensor, which to measure the total concentration of dissolved salt for fertigation precisions, and last but not least is pH sensor to monitor the acidity of the nutrient solutions. So move to the next major component, which is actuators. So this is a physical component that carry out the commands issued by the PLC. So there is two primary mover, which is main irrigation pumps, uh, which act to deliver the water, and another one is high precision injector pumps that control the speed to inject concentrated stock nutrient into the main water line. So for the uh, actuator, we also have solenoid valves. These act as automatic gates which open and close the flow paths. It also divert water to specific irrigation zone. So the last major component is hydraulic system, which the scope for this hydraulic system is actually all infrastructure that storing, preparing, and distributing the fertigation solutions. So for storage, it includes the water storage tank and separated tanks for concentrated stock fertilizer solutions. Uh, for preparations, it actually a series of filter that remove contaminants. Its goal is to protect delicate pumps and prevent clogging of drip emitters. So uh, and it also hydraulic system also responsible for distributing, which include the network pipes and drip lines that carry the nutrient and water to the plant root zone. So this hydraulic system design goal is actually to ensure uniform pressure and flow so that every plant receive the prescribed amount of water and nutrient. So this is the sequence of the automated fertigation cycles of our project. So first of all, we have the monitoring and initializations. So this is where the PLC is continuously monitoring the state of the soil. It constantly receives data from the soil moisture sensor and compares the current moisture level against a preset critical threshold. So it also checks essential condition such as schedule time, whether the water supply is needed or not before proceeding with anything. So during this monitoring and initialization, the PLC will determine whether an active fertigation event is required or not. So moving on, uh, after PLC detect that active fertigation is required, the irrigation starts from the input sensor. So it's triggered when the soil moisture drops below the minimum allowable threshold. Uh, and then the PLC send a signal to close the relay, activating the main irrigation pumps. So pumps draw water and push it through the main pipes, and PLC also energize solenoid valves to open the path to the designated irrigation zones. So along the line, a fertigation dosing occur after irrigation starts. So as water pass through the sensor array where the EC and pH sensor take place, it compares real-time reading with the program target set points. If EC is too low, the PLC activates and modulates the speed of high-precision injector pumps to inject fertilizer. Fertilizer is injected until the EC reading match the target set point, and this similar process occur for the pH using acid or base solutions. So after all is done, irrigation is stopped. So PLC constantly monitor the flow meter and elapsed time cycle. So when the program volume or time set point is reached, the PLC immediately de-energize the relay. Those shut down the main irrigation pumps and injector pumps, stopping the flow. After this irrigation stop, there will be another process for post-fertigations. There is another process for post-fertigation flush. PLC runs the main irrigation pump again for a short time, but the injector pump remain deactivated. The purpose of this is to flushes plain water through the systems to prevent salt crystallization, biofilm buildup, and emitter clogging to maintain this system efficiency. And lastly, the system return to standby mode. We shut down all active components and PLC de-energize any remaining open solenoid, isolating the irrigation zones. The PLC remains powered and return back to the first sequence, which is monitoring and initializations, and ready for the next autonomous cycle.
Okay, so my name is Wan Hafizudin, and for my part is system block diagram. So the system begins by establishing the idea of gold standard for our soil condition. And in this project, the system set a specific targets where the pH level must be between 6 and 7. The moisture level needs to be at least 25%, and the nutrient levels of NPK must be above 30%. So once all these three rules are set, the system enters a continuous loop where it constantly reads the sensor to find out the current pH, moisture, and the nutrient levels of the soil. So based on this measurement, the system makes decision to correct any problem. First, it checks the pH. If the acidity is outside the safe range, either too high or too low, then the system will activate pump 1 to flush the acidity or the alkaline inside the soil to adjust the pH of the soil. So and simultaneously, it also check the nutrient level of the NPK. If it's too low, then it will turn on the pump 2, which will add the fertilizer for a set amount of time. Then it turns on the clearing valve. By turning on the clearing valve, the pressure of the inside the main pipeline will be dropped, and this will clean the inside of the main pipeline from clogging with the excessive fertilizer inside the main pipeline. So finally, the system also ensures the plant will get enough water. It checks if the soil moisture is below 25% target. If the soil is too dry and while having a stable pH correction, it triggers the moisture sensor and activates pump 1 to water the crops. So after this watering cycle is complete, the entire process will look back to the beginning to measure the soil again, ensuring the crops are monitored around the clock. So that's all for my part.
Okay, so we go to the PLC ladder diagram. So this is the PLC ladder diagram that the initial condition without any interruption, which is the pH value is at 6 or 7, and the moisture is at the good condition, and the NPK sensor also don't need to active since the NPK is at the right amount. So we go to the first scenario, which is the pH is going down, which is become acidic. So when the pH become more acidic, it will detect the pH minimum and it will active the pump one. But before active the pump one, it must to um, check is it pump two is off or not. So if the pump two is off, so the pump one will be on. So to this next scenario, which is the pH max is at the 7 and above, which is at the alkaline. So same as before this scenario, which is it will check first is it pump 2 is on or not. If not, so the pump 1 will be on to rinse the plant, to rinse the soil. So we go to the next scenario, which is the moisture scenario, which is if the moisture below than 30% from the soil. So same goes as the pH and pH max and pH min, which is it will check first the pump two is it on or off. Is if the pump two is off, so it will on the pump one, which is to watering the plant. So we go to the next. Okay, for the next scenario, which is if the NPK concentration is low, so it will trigger the NPK sensor. So the NPK sensor will be active, and the NPK sensor will check is it pump one is on or not. If not, so it will start the timer one, which is to indicate how long that the pump two should be active. So pump will continue active until the timer one is off. So next, when the timer one is achieved in time, so it will go to the round three, which is at the round three. It will trigger the round three at the timer one, and it will active the valve. The function of this valve is to open the end of the tube at the watering system to rinse the what we call to rinse the fertilizer that we use to ensure not have any accumulation or crystallization on the pipe. So if it will open the valve, in the same time it will active the pump one. So the pump one will deactive until the timer two is on at, is at the end. So after the time two is active, so it will trigger to off the valve and also the pump one. So that's all for PLC diagram.
Finally, as a conclusion, our team has successfully accomplished the design and documentation of a hypothetical PLC controlled fertigation system and completed the objectives and deliverables of this project, which includes a preliminary literature review on existing systems, a general list of major components required for this system, a sequence of events, and a ladder diagram. This project has provided valuable insight into the application of sensors and transducers, as well as the design and implementation of a PLC ladder diagram for real world use cases. So, following the completion of our project, there are several key areas where a future continuation of this work could expand or improve upon. So, these recommendations are fabrication of a basic physical prototype. So, while our project focused on design and documentation on paper, building a small scale prototype would help validate the control sequence, ladder logic, and system flow under real operating conditions. Next, a cost benefit analysis would help to compare between manual fertilization and a PLC controlled system. This will help quantify potential savings in labor, water, and fertilizer usage. So, this will help support the feasibility aside from just theoretical implications. So finally, we would like to include a more detailed evaluation of actual components. So in our project, we did a very surface level overview of what components we would have, but a future study could help review real sensor, pump, and valve specifications, make and model to help determine their suitability, performance limits, and reliability for integration into the fertigation system. Thank you once again for your time.